Okay. How's it going, guys? This is Gerardo with video solution number 4. And, well, for the last solution, I got problem number 4. And, well, today I came to solve the problem. Well, and I'm gonna show you my approach to the problem. Okay, so the first thing we have that we've made it to the finals of the Science Olympics. Woohoo! Uh, Good for us. And then, as one of your tasks, you're given 1.0 grams of aluminium and asked to make a wire. Okay, so here we're given 1 grams of aluminium, which this is very important. Oops, I'm not left-handed. I'm sorry. There we go. And then and we're asked to make a wire. So make a wire. So I guess we have to expand it and then give it a form, even melt it. And it says that using all of the aluminium, we have to use all of it. We cannot have any rests, we have to use all of it. Okay, so using all the aluminium, then this problem is asking us that we are connecting a battery, a 1.5 battery, to the wire, and our wire should dissipate 1.5 watts of power. Okay, so I'll read it again. Using all the aluminium, that will dissipate 1.85 watts when connected to a 1.5 volt battery. Okay, and so question A, I'm sorry, asks, what diameter will you choose for your wire? And B, what length will you choose for your wire? Okay, so I guess this is pretty clear. We have to find the diameter of the wire that we have to make, given that there's a 1.5 wire, that there's going to be a 1.5 volt battery connected to it, and that it should dissipate 1.85 watts of power. And then once we have the diameter, we can find the length. So that's basically it. So here this is a representation of it. We have like a piece of aluminium, 10 grams of it to be specific. Well, I'm sorry, not 10 grams. 1.0 grams of aluminium. And basically we have to find this diameter and all this length, which we're gonna call L. Okay, as we can see, like if we zoom in into the picture of the wire, we have that it looks like this, and we're gonna assume that we are, well, of course, we made it to the Science Olympics. We can make this a perfect cylinder. So we're gonna make it a perfect cylinder with a diameter of D. Okay, so here's my approach to it. You can read it. So, and then I'm basically saying that we have multiple equations related to one another, but in our case, we're not gonna solve the answers in order, and we'll see why. So the first equation that relates power, length and resistance, and you'll see why I chose this, is the resistance is equal to the resistivity of this aluminium times the length of the wire, which we want, times the area of a cross-section of this cylinder. So right here we have two of our variables that we have to find, and we can express this in terms of radius. Resistance is equal to resistivity times length divided by pi r squared, which in our case is the area of this circle right here. Now, we don't really want the radius, we want the diameter. So we can just basically substitute it. Let's remember that the diameter that the radius, that the diameter is 2 times the radius, and that's always that's a given. Now, we also have this equation, which is power is equal to the voltage squared divided by resistance. And this is kind of why we chose this to work with, because we're given a what is called a relationship between power and resistance. And resistance, we don't really need it, so we can substitute it. So right here, for the power, we have we're gonna denote it P. Voltage is V, and resistance is R squared. So P is equal to V squared divided by R. Okay, and now we substitute resistance for power, and then we get this equation. Now, these are our givens. We have 8.5 watts of power, 1.5 volts in the battery. And then here's the thing. The material in this case is very important because, as we can see in our equation, we have resistivity. And every metal has its specific resistivity. Now, also, it gave us the mass. And well, since I'm a chemistry major, I'm a biochemistry major. Every time I'm given mass and I have to work with volume, I always think of well, you'll see what I always think of. We have the mass, that's very important, and then the resistivity, which is just a constant, 2.8 times 10 to the negative 8 ohms per meter. Okay, and then we'll go with the following. Okay. Yes, so B. As I mentioned, we are not gonna answer them in question. We just skipped A. Okay, so as I was saying before, we have two equations with the same variable. We can just set them equal to each other since the resistance is the same for the wire. Now we have one expression for resistance, which is a resistivity times the length of the wire divided by pi, diameter divided by 2, which is just the radius, and that's squared. And then we have another expression, which is resistance is equal to voltage squared divided by power. Now, since they still have resistance for the wire, then we can set them equal to each other. Now we have a final version, which is V squared, voltage squared divided by power, is equal to the resistivity times the length divided by pi, radius squared. Now, as we can see, we still have two unknowns, and we only have one equation. So that's kind of bad for us. Okay, so for now we're just gonna change it for R, which is this equivalent, so we don't have to work with multiple variables. Okay, so you can read this. This is my approach to it. Okay, so we can analyze this equation, and first we have to find the area of a cross section for the wire, this cylindrical wire. And we also have to find the length of it, but we're not given any of those. Well, we know that for the area of the cross section, we need the radius or the diameter. And for the length, well, we have to calculate that. Now, here's the thing. If we cut the wire like in very tiny pieces, we'll have, if we cut it in infinitesimal pieces, like infinity, it's kind of analogous to the definition of the integral. Like, as we can see, if we take one piece of wire with the diameter d, and then add it to another piece of wire with the diameter of d, which is, if we have like a, let's say that it has like a, what is it called? It is thick, its thickness is defined as DL. And we know that DO is just like it's very, very, very small change in length. Because the wire has a length, and that's kind of what we saw over here. It has a length, and it has a diameter. So if we cut it, basically we can call those tiny pieces of length dl, and then well, all of them are going to have the same diameter. Okay, so if we do this and we do it infinite times, we'll eventually get a piece of wire with a length L. And this is very important. Because if you think of an integral, the integral is just taking very, very small pieces of area, well, the area integral, very, very small pieces of area, and then it's turning them into a whole. And I don't know if you had volumes of rotation, but this is basically the same. If you've seen volumes of rotation, I'm sorry, but this is basically the same. So if we take these small pieces of area and then we add them, we'll eventually create a volume. Okay, so this is basically saying that the area times the length, because we have multiple amounts of dl, and if we add all of them dl's, we'll get the length. So the area times the length is equal to the volume, and we can see that we created a volume right here, but just adding the multiple areas, and then infinite amount of times, L amount of times, length amount of times. So this is kind of basically the definition of a multiplication. When we add stuff multiple times, we have area times the length is equal to the volume. Okay. Now, and this is very important. So right here we have our expression, and we can multiply it times 1. Because 1 will not change anything, right? If we multiply anything times 1, it won't change its value. Maybe its form will change, but not its value. And that's kind of what we want. So if we multiply it times L divided by L, we'll get the resistance is equal to the resistivity times the length squared. And this looks familiar. This looks familiar. Area of cross section times length. We just saw it. This is gonna be the volume of the wire. That's very important. Okay, so we have that the resistance is equal to the resistivity L squared divided by volume of the wire. And as I mentioned before, we are given mass, and every time we're working with mass and volume, since, well, I think this is a good thing to study chemistry, because every time you're given mass or volume there and you kind of want to relate them to each other, you find density. Density, very important, is specific, just as resistivity is specific to materials, depending on, well, specific to materials, to elements. They will always take the same amount of space per gram of material. Okay, so we have the density is equal to mass divided by the volume, and this is like the basic formula for it. And if we apply the density of aluminum, we'll get that the volume of aluminum is equal to the mass of aluminum, of the sample, I guess, divided by the density of aluminum, which is, well, that's a given. That's constant everywhere. Okay, so, and this is kind of what we're answering part B first. Like, for me, when I was answering this, I wasn't really going in order. I was just playing around with the formulas, and I saw that it was more convenient to solve part B first. And we'll see why. Okay, so resistance equal to resistivity L squared divided by the volume of the sample. Now we can substitute that mass of the sample divided by the density of aluminum, and we'll get this. And now, as we can see, we don't really have any variables, any unknowns besides the length of it, the length of the wire. And this holds true because we're using the mass of the wire and then the density of aluminum. So by giving the mass of the wire, this kind of holds it to be one certain amount of material. Like let's say the mass here and the denominator kind of adjusts the value of the length because we don't really have what is it called a great amount of material, I would say. We can explain it better here. Okay, so we basically solve for L, and right here we have the square root of the voltage squared times the mass, and then divided by resistivity, density, and power. As I was mentioning here, the length is proportional to the square of the mass of the sample, and this makes sense because if we have a greater amount of mass, we have... Okay, I'm sorry for that. Apologize, inconvenience. Okay, so where was I? I was explaining that the length is equivalent to the square of the mass of the sample, which in our case we have 1 gram. and well, I was saying that this makes sense because if we have a greater amount of mass, we can make a what we can make a longer wire. Yeah, that's the word to it. Okay, so we basically have the equation to it. As we can see, there's no negative lengths here, so we're going to use a positive solution to this. And we can just basically plug in the numbers. Okay, and we'll see this. Okay, so we have that the length is equal to the positive solution of v squared, the square root of everything inside here, which is the voltage squared, times the mass of the sample divided by the resistivity of aluminium, density of aluminium, and the power that is dissipated in the sample. So if we plug everything in, if we evaluate with our nodes, which we know everything of this, we have a length of 1.87 meters. Okay, and this was the first part to it. And now we can go on to solving. And there's now knowing the length of it. It's basically, since we have the amount of material and the length that it is supposed to be, we can easily find the area of the cross section and therefore the radius of the cross section, or the radius of the wire, I would say. Yeah, of the cylindrical wire. Okay. So as we can see, we'll go back to the original equation, the one we had here. We squared this, and we basically just solve for d. So do some algebraic manipulation. We basically get that this 4 passes on to the numerator, and then we get this expression. We substitute that 1 in the denominator. Times, we can multiply this times this, and then divide this side by r and multiply it by 1 over r. Since we're dividing over here by r, we have to do the same thing on the other side. Sides switch. Basically, we just have that the diameter for the sample squared is equal to 4 times the resistivity times the length, and that divided by the pi times the resistance of the wire. And now we can just take the square root, as I mentioned before. We don't really have negative measurements, so we're gonna use a positive solution to this. We just evaluate now that we know the length of it, and we get a diameter of 5.0 times 10 to the negative 4 meters, which is basically 0.5 millimeters. Yeah. 3 and 1. Yeah. Okay. So now, this does make sense, and I believe it does. We have the correct units for both questions, and as I was mentioning before, the equations do make sense. And why do they make sense? Because they're bound to some limits. And as we can see right here, we cannot have we basically found out that the length is proportional to the mass of our sample. And this makes sense because if we have a greater sample, we can make a longer wire. Now, as we can see, it is inversely proportional to the square of the power. And what does this mean? So as we increase the power, the length decreases. Now, as we increase the power dissipation for the material, for the wire, I would say, the length decreases. And this makes sense, because if we have a shorter wire, that means that it can heat up quicker, like very rapidly, and it will produce heat, which is power dissipation, basically. So that part makes sense. So now let's go on to the next one. Does A make sense? Well, I believe it does, and again, this is proportional to a length. If we have a greater length, which, as we saw, if we have a greater length, that means that we have a greater amount of sample. And if we have a greater amount of sample, the diameter can increase, the thickness of it can increase given a specific length. Okay, so I guess that is everything for this. Thank you for watching, and I'll see you on the next one.